Hello students, welcome to Wallah English channel. In this session, we'll be practicing many questions on Turing machine as well as undecidability questions. Okay, so you have learned what is Turing machine and what are the types of Turing machines, as well as um, we have learned recursive versus recursively enumerable language. Now, um, we will see some of the questions on identifying the languages or problems which are decidable and undecidable, along with some Turing machine questions. Okay, the agenda is like you should aware of the Turing machine decidable problem or language RE but not recursive, as well as not RE. Then we'll see some practice questions that you will get always as homework questions. Okay, so now after this subject you might have a doubt what subject we are going to start. There's a DBMS by your favorite faculty Vijay sir, and it is starting from 29th March and day after tomorrow from 4:30 to 5:30 p.m. Okay, this is the next subject you will be having as a DBMS. So you can mark it. The database is going to be started by the Vijay sir from 29th March from 4:30 p.m. to 5:30 p.m. Okay. Now you may ask questions, sir. If you have learned all the basics in TOC, now what else is needed to have a revision and practice? So I recommend you to practice all the gate questions which are there and try to focus on them, and also learn some of the important topics which are not covered here, and that's very important. Yes, Seema, good evening. Okay, please mark the next subject database from 29th March. There is a day after tomorrow, and tomorrow you will not have the session on TOC as well as DBMS. So you are going to have this session, DBMS session, from the day after tomorrow by Vijay sir. Okay. Now in this Turing machine and disability, we have covered or we have discussed various topics, right? In this mainly, you have the TM, HTM and LBM, three types of machines, and also the main languages that we have studied, recursive and recursively enumerable languages, right? Recursively enumerable problems and languages. Now when it comes to decidable and undecidable problems, we have seen some decision properties table. There you have 8 problems for every category, like for finite, for PDA and so on. What kind of problems we have studied there? Halting, membership, emptiness, finiteness, totality, equivalence, disjoint, set containment, and various problems we have studied in the decidable and undecidability chapter. Okay, let's start with the first question which you have seen in the PYQs, that is, which of the following statements is or are true? Okay, you need to identify the true statement. So can you try this? Which statement is the true here? Every subset of a recursively enumerable language is recursive. Can you guarantee every subset of recursive enumerable is recursive? You cannot guarantee even subset of RE is RE, because the subset property is not closed for regular CFLs, DCFLs, recursive languages and RELs. So now subset of recursively enumerable need not be recursive, then we cannot guarantee it is recursive. Okay, so actual statement is like every subset of recursively enumerable language need not be recursive, or you can say some subset of recursively enumerable language is recursive. That could be fine. If I keep this every with the sum, this statement will be correct. This statement will be correct. Okay, even I can say some subset of recursively enumerable is regular. You can say that too. Okay, over any sigma that you take, then the statement could be easy to understand. Right now it is a false. It is false. If a language and its complement are both recursively enumerable, that means L has a Turing machine, even L complement also has a Turing machine, then you can build alternate Turing machine for L. So this is not only from L and L complement are REL. Now you can also write in converse direction, L is recursive implies L and L complement should have Turing machine. So this is very interesting. Not only this way, in the converse also it is true. This statement is the true statement. Now we need to identify the true. We got the true, but it is MSQ type, so more than one option might be, more than one option may be correct. Complement of context free must be recursive. Complement of context free is need not be context free because it is not closed operation, and complement of context free you can always guarantee it is a context sensitive. The reason is the context free language is closed under complement, so CSL complement is always CSL, so every CFL you can assume it is CSL, so definitely complement of context free must be recursive because it is already context sensitive language. So this is also true statement. There is another true statement is complement of context free must be context sensitive. That statement is also true. Okay. Next, if L1 and L2 are regular, there are two regular languages, then intersection of two regulars must be deterministic context free. So here students may study like regular intersection regular is regular, but instead of giving regular, here it is mentioned DCFL because every regular is a DCFL. In fact, it is must be regular, but instead of regular they mention it is deterministic context free. That is also true because every regular is a DCFL. It is also true statement. So what are the correct statements here? That we have B, C and D are true statements, and only first option is false. Only first option is false. Okay. And there are very interesting points that you can note down here about the subset. About the subset I am writing here. About the subset, every subset of finite set or finite language is finite. Here every subset of regular language is may or may not be regular. Not only this, you can also write may or may not be CFL, may or may not be DCFL. Even subset of regular, no guarantee of even recursively enumerable. So this statement is enough to say that every subset of recursively enumerable need not be recursively enumerable. Okay, so this statement itself is a very big statement. Every subset of regular is may or may not be regular, may or may not be CFL, may or may not be DCFL, may or may not be recursive. So many answers are there for even this line. Yes, Sudeep, good evening. How are you? If I say some subset or some subsets of regular language are, okay, if you are taking only subset, that's you will use a singular statement. Some subset of regular language is definitely regular. Even you can write even finite also possible. Okay, some subset of regular is finite, some subset of regular is infinite, some subset of regular is regular, some subset of regular, okay, need not be non-regular, because if you take a finite language, subset impossible to be non-regular. Okay, so you need to understand what way you can write. Some subset of regular is, even you can write finite. Some subset of regular is infinite, but you cannot guarantee some subset of regular, some subset of a finite. Okay, I'm talking about this one. Some subsets of finite is not regular, impossible. Some subset of finite is non-regular, impossible, but some subset of regular is non-regular is possible. Okay, is non-regular is possible. only when it is infinite language. So here even when you apply this, right, some subset of regular is not regular, this statement could be false, because if that regular is the finite, in general is true, some regular, some subset definitely possible non-regular. But if I give you particular regular, can you say some subset of regular is non-regular? May or may not be possible. Okay, so that's I'm not writing the last line. What context you are writing it is some subset of some regular is non-regular possible. But if I give you, let's say, finite language, some subset of that finite language, you cannot write non-regular. Okay. Yeah, Sima, your video is buffering. I'm good, Sudeep. Let's try the second question. Meanwhile, I'll check why the video is buffering. Is it buffering? Oh my god. It looks fine here. Maybe network issue, something like that. Okay. Which of the following is or are undecidable? So now you need to understand undecidable statements here or undecidable problems here. Given two Turing machines, if I give you two Turing machines, can you decide the languages accepted by them are equal? That's equivalence problem. If you want to understand which problem it is in decision properties table, equivalence problem for Turing machine. Equivalence problem for Turing machine. Is this decidable? All the problems that we have studied are undecidable in the decision properties table, right? So this is undecidable. It is MSQ. Option A is true, but we need to go for remaining undecidable also. Given TM, is it really accepting a regular? So if Turing machine given to you, can you guarantee or can you check that Turing machine is representing a regular language? We do not have any kind of generalized algorithm to check the behavior of the Turing machine. Even you cannot understand whether given string is accepted or rejected by Turing machine with the generalized algorithm. So this problem is non-trivial property completely, right? It is also undecidable. It is also undecidable. Okay, like given TM, is it accepting finite language? Is it accepting regular language? Is it accepting infinite language? Is it accepting context-free language? Is it accepting context-sensitive language? Is it accepting recursive? All problems are undecidable. But is given TM accepting recursively enumerable language? That is trivial problem, decidable. Every Turing machine in the world, it has to accept a recursively enumerable. But you are not asking specific language. That's why the given TM accepting recursively enumerable or not is decidable. Only for recursively enumerable in place of regular, if recursively enumerable is given, this problem is decidable because it is a trivial problem. Okay. Now both are undecidable so far. Given Turing machine, decide if M accepts all string. It's a totality problem, completeness problem, totality. Completeness problem, that is language accepted by given TM is equal to sigma star. Accepting all strings or not, you need to verify. So is language accepted by TM sigma star? That means is it accepting every string? So this is also undecidable. This is also undecidable. The given TM, decide now if M takes more than 1073 steps on every string. Now this one, now the steps are given, right? 1073 steps, more than 1073 steps on every string. If you want to verify on every string, you don't need to verify on every string. Just verify up to 1073 length strings, 0 length to 1073 length. So length of W equals 0, 1 up to 1073. This all the strings verify, are they taking? If all strings here, all strings from 0 to 1073 length, from 0 to 1073 length takes, now you want to verify more than, right? Takes 107 fourth step. You don't need to go even beyond that. That means not only this strings 1074 length, 1075 length, everybody has a prefix of 1073, hence remaining all will also take this 1074 steps. So now you have finite number of strings. Now you need to verify up to finite moves only. That is why this problem is going to be decidable problem. Even the question has every string you have to verify, but we don't do that. We do up to 1073 length. We'll verify every string should take 1074th step to say that machine takes more than 1070 steps on every string. Okay. If any of the string is halts before 1074th step, that means that machine is not going to satisfy the given property. Yes, A, B, C are decidable, sorry, undecidable. C is, sorry, D is decidable. Okay. Yes, Sham, you're right. Okay. This is very famous type of gate question so far. Multiple times asked a similar kind of questions. Which of the following languages are undecidable? Again, you need to identify just undecidable, decidable, undecidable. Only two things you need to verify. So now M is here, Turing machine. So what is the first one? Represent, second, third, fourth. All four languages are given. So what problems will help you to understand these four languages? So each language depends on some particular problem. If you have studied the first language, if you have studied the first that is emptiness problem, then L1 is depends on that problem. So is that given Turing machine accepting nothing? Nothing means empty language. So this actually represent emptiness problem. If you know the concept of emptiness problem, you give the same answer to this language also. Now what is the emptiness problem for Turing machine? Is undecidable, hence this language is also undecidable. This language is also undecidable. Undecidable is right. Next one. Now you have the Turing machines. Now W also given. So W is given, machine is given. Now is it able to reach the state queue in exactly 100 steps? In exactly 100 steps. Now see that these steps are not given, then this could have been undecidable. But now you need to verify exactly 100 steps only, not more. So you will never go to infinite loop. You are going to halt infinite time. Halts, the algorithm, the logic halts infinite time. Logic halts infinite time. You need to verify only 100 steps. Now the W is given. What is given? M is given, W is given, Q is given. Now what is your problem? What is your algorithm? Your algorithm should just run the string on this machine, and you need to run exactly 100 steps. The algo runs exactly 100 steps, not more, not less. Okay. In exactly 100 steps it is going to run, and if Q is reachable or not, you are going to decide. So this you can easily say yes means the Q is reached, no means Q is not reached in 100 steps. That's all. So you have an algorithm for this. Yes, B is decidable because of that 100 steps. If 100 steps not given, this problem could have been undecidable. The reason is before reaching Q itself, it might go into infinite loop and you never halt. You may never halt. Then this is not algo. Algo is not possible in that case. If these 100 steps are not given, then algo is not possible. Maybe you can design Turing machine but not halting Turing machine. So B is this decidable. Now see, Oh, language accepted by Turing machine, is it recursive or is it not recursive? Is it regular? Is it not regular? Is it finite or is it not finite? All such problems are not decidable, undecidable. Okay, they're all non-trivial properties. Now, next, language accepted by M contains at least 21 members. At least 21 members. If it is not accepting, or if it is not accepting, the machine is not accepting any string, then the language could be empty. But if it is having at least 21 members, yes, you may provide a logic, but no impossible. Anyhow, this problem is going to be undecidable. Undecidable. Okay. But it is partially decidable. Those machines who are able to accept at least 21 members, you can find them. But if any machine is not able to accept at least 21 members, you may not have a logic for them. Okay. Anyhow, even though partially decidable, it is undecidable. You will have a Turing machine, but you can't build a halting Turing machine. You can write a program, but you can't write algorithm. So that's very important. So L4 is undecidable. Now L1, L3, L4. L1, L3, L4 are undecidable. Okay, you need to identify undecidable. Yeah, for RE language, a membership problem is undecidable, correct? But this is not the membership problem. This is looks like a membership, but when you run the W, you have another target, whether you are able to reach the state queue in exactly 100 steps. So here you are going to put a limit how long you are going to run the string. Okay. Next, can you try the next one? You have the problems, 4 problems here, and L of G denotes the language generated by a grammar. L of M denotes the language accepted by machine. Okay, by default the grammar, if they don't mention any grammar, it is unrestricted. If they don't mention the name of the machine, it is Turing machine. Okay, yeah. Can you find out these 4 problems quickly? Yeah, I'm reminding again, from day after tomorrow you will have the DBMS, and DBMS is going to be started by the Vijay sir. Okay, from 29th March, timings 4:30 to 5:30 p.m. So please attend the database classes by Vijay sir. Okay, next, first problem. Given unrestricted grammar and given string, oh, here this is called as membership. Now W belongs to, this is REL, right, recursively enumerable language. So membership problem for recursively enumerable grammar, membership problem for recursively enumerable language. Yeah, Seema. Right now it is the last class. I know I have covered basics for each chapter. Now the practice sessions will come, after covering many subjects. I'll come up with the practice sessions later. Okay. Right now it is the last, but we never end up with any, basics. We just completed the basics. Now at the end of the maybe September or October, we'll start some practice sessions. There we will have so many questions to practice. Now already almost this is the 17th lecture. Each lecture have given 5 assignment questions, and at least you practice this 5 questions in each lecture. Apart from what I have explained, right, you will see there almost more than 80 problems. That is very good amount of problems to understand and to have the basics. And overall I covered, I think, more than 200 problems so far. So nearly 300 questions you can find only in this session, 17 lectures, which will be really good beginning to start. The first one is a membership problem. Membership for Turing machine. Membership for Turing machine is undecidable. Right now you need to identify what following statements are correct. Okay, this problem is undecidable. Next, for given Turing machine, whether, again repeating, did you see that? Did you see that? Very similar questions. If you are able to understand, many people even without understanding also they can remember it, some of the points because you are not able to acquire that concept. See that language accepted by Turing machine is regular, you need to understand. How do I know that what a language accepted by given Turing machine except recursively enumerable, right? You can only understand the given Turing machine is accepting REL, but you will never understand is it accepting finite or infinite, regular or not regular, CFL or not CFL, right? This is again non-trivial property you are looking for, that is undecidable. And given two grammars, are they accepting, are they generating, are they representing same language? This is equivalence problem for Turing machine. This is also undecidable. Last one, whether there is a deterministic PDA such that N and P accept the same language. But what is given? NFA is given, only NFA is given. Now you need to identify writing your own algorithm. Now you need to have an algorithm. Algo to find there is a DPDA, Algo to find DPDA such that, and let's say this is a D, this is N. Language accepted by N is equal to language accepted by D. Yes, you can always find. There is no statement no here. It always yes, because every NFA you can convert. Every NFA, see what I do. This is algorithm, right? In algo what I do, you see it. I'll convert to DFA, and every DFA I can convert to DPDA. You have an algorithm too. And now, see there exists, right? Now this has to accept the same language. I found the DPDA, right? Now these two definitely accept the same language. So now that's enough. That's enough to say yes. Given NFA, convert to DFA and say that I have a DPDA. By converting every DFA to DPDA, how do you convert? So go to every input symbol, write Z0/Z0 additional 2 parameters with along with every input. So that makes DPDA. That means every NFA you can find a DPDA. That is simply what they are asking. What are they trying to ask? Do you have an algorithm to convert every NFA to DPDA? Yes. This is a decidable. What is this? It is decidable. Every NFA you can convert to DPDA. That's enough to say that this problem is decidable. Okay. Now, how many are undecidable except last 1, 2, 3? Do you have the statement? Yes. That answer is D. Last option is here. Only 1, 2, and 3 are undecidable. Yeah. Yes, except D. All are undecidable. All are undecidable. Fine. Yeah. Let's go to the next question. The set of all recursively enumerable languages is dash. Closed under complement, intersection. What? Is it a subset of the set of all recursive languages? Is it uncountable set? What is the right statement? Very easy. If you know the first two options, that would be enough. It is already MCQ, right? Even though you don't understand the last two, the first two you already have an answer. That is, it is not closed under complement, right? If you remember that recursively enumerable languages, if you try for complement and then intersection, for complement it is not closed, but intersection it is closed. REL intersection REL, you will always get REL, and you can design a Turing machine for the intersection operation of two RELs. Now from this two you got the answer closed under intersection. But some people want to understand more, because this question might be MSQ. Then how do you answer it? MCQ you have no issue, you got the answer. So you can blindly choose B without understanding C and D. But if it is MSQ, then you need to understand every option that you have. Now the last one, the third option, a subset of the set of all recursive languages. Now you see that set of all RELs, that is the type 0 class, set of all RELs, is it subset of or superset of? Is a superset of the set of all recursive languages. But here it is mentioned the subset, that's why this statement is wrong. It should not be subset, it should be superset. The set of all RELs is a superset. Yeah. And now the next one, the set of all RELs is actually a countable set. Set of regulars, set of CFLs, because we have the one-to-one correspondence with the some version that you can map, right? It is actually countable set. Because of this, it is wrong. It should be a countable set. Set of all RELs is a countable set. Every REL you have a TM, and every TM accepts a particular REL. That makes you will have the bijective mapping with some countable set to prove this is a countable. Okay. Next. Yeah, can you try this question too? Yeah, almost every question looks like the previous year questions, because most of the questions are similar, except one or two statements that you see. Yeah. Can you try this one? You have a language represented by regular expression R, and you also have a language generated by context-free grammar, and you also have a language accepted by Turing machine. So M represents Turing machine, G represent the context-free grammar, R represent regular expression. They mentioned, right? Which of the following decision problems are undecidable? Only undecidable things you need to identify. First statement is a membership, right? It is just membership for regular languages, as you are talking about regular expression here. It is decidable, we are aware. And the second one is emptiness for the context-free grammar. Emptiness is a given grammar accepting nothing, is a given grammar accepting empty language, or is given grammar generating empty language, is given context-free grammar is generating nothing. It's about context-free language. It is about context-free language. Okay. So emptiness is also decidable. These two problems so far decidable. And third one, given context-free grammar, is that context-free grammar generating every string like sigma star? Totality problem. Totality problem for context-free language is undecidable. If you remember that totality for context-free languages is undecidable. Totality for deterministic context-free languages is decidable, but context-free languages it is undecidable. D. So this is undecidable. Okay. You are looking for what? The undecidable only, right? 3 is undecidable so far. And given TM and string, oh, is it membership? Yes, the membership for Turing machine is also undecidable. So 3 and 4 are undecidable. 3 and 4 are undecidable. Okay. 3 and 4 are undecidable. Yes, option D is right. Option D is right. Yeah. So this is also one of the famous question about the operations, like closure properties. When you study these operations, you should understand what kind of conclusion or language comes out when you do or when you perform the operations. Yeah. You have the different types of languages like regular, context-free, recursive, recursively enumerable. Which of the following are true? So you need to identify the true statement. Okay. Can you try? Okay, you just do the substitutions, like remembering L1, L2, L3, L4 might be different. Substitute immediately. Recursive complement union REL. Recursive complement union recursively enumerable. Now what is it going to be? Recursive complement is recursive union RE. Recursive union RE, you can always say RE because for both of them you have a Turing machine. You can do the union for union of two languages to get the another Turing machine. So this is the recursively enumerable, but need not be recursive. So this statement is true. So this statement is true. One is a true. And two, L2 complement. What is L2? CFL. So CFL complement. union, that is recursive. L3 is recursive. CFL complement, you can always say CSL, or you can say recursive. CSL union recursive, you can always say recursive. There is no issue with the recursive. Yes, it is always true. Now the third one, L1 star intersection L2. What is L1? Regular. So regular, clinic star of regular or clinic closure of regular intersection with the CFL. And if you look at the regular clinic closure property is closed for regular, so you will always get a regular. Intersection CFL. You already know the regular closure is also closed for CFL when you perform union and intersection. So CFL intersection regular is always CFL. Now the question is, the statement is also same. It is the context free. 3. Fourth one, L1 is regular union, L2 complement is a CFL complement. We know CFL complement is need not be CFL because it's already not closed property. And regular union, you get a context sensitive language always. You can say context sensitive language, but you cannot say context free all the time. So this statement is a false statement. False statement. So 1, 2, 3, which is going to be the option D. Yeah, option D is right. Can you try the next one? For any two languages L1 and L2 such that L1 is the context free. Similar question, right? It is also one of the gate questions. L2 is the recursively enumerable but not recursive. So you need to remember that this is a special language. RU but not recursive. Which of the following are necessarily true? Means which of the following are true? Okay, CFL complement is recursive. Is it true? We are going to identify the true. Yes, it is true because complement of CFL is context sensitive always, so recursive. It's how many times came so far? 3 times the same kind of property. Okay. L2 complement. Oh, L2 means RE but not recursive. Complement is not REL always. If you do L2 complement, you should get not REL. But here it is mentioned as recursive. Because of that, this statement is wrong. L2 complement has to be not REL because RE but not recursive complement is always not REL. Okay. L1 complement is context free is wrong because it should be context sensitive. L1 complement union L2. L1 complement, you got a context free complement is context sensitive union L2. L2 is already RE but not recursive. So both you can assume RE, you get RE always. So this statement is true. Context sensitive union RE but not recursive, both will have a Turing motion. So you can prove that the union will have a Turing motion. So 1 and 4, that's going to be option D. Option D, yes. Option D, correct, Sima. Sham, right. Okay, theoretical question. See that you just need to apply your concepts. Nothing to use the pen and paper. Everything you can understand from the question itself. You should have a knowledge of these closure properties, and you should have the knowledge of various problems you have studied in decidable and undecidability concepts. Okay, which one of the following problems is undecidable? Again, undecidable. Deciding if a given context free grammar is ambiguous. It is ambiguity concept for context free grammar. No, Sima. Only one question was there, I think in the last 20 years so far. You just see one question. Construction based questions are not there. Diagram based questions, only one is there. That's very rare and could not be expected in the gate such questions, because the Turing machine somebody designed and you want to understand may take much time. Okay, you may predict 1 or 2 states or 3 states max, but that too easy question. In the options they will provide, you just need to match. Okay, even though they give it. So ambiguity problem for context free grammar is undecidable, right? This is undecidable. Okay, I'm just putting the tick because it's already undecidable. It's MCQ, that means you got the answer. Remaining should be decidable, as you got the first one is decidable in the exam. It's a time saver, right? You got the answer, you are confident about it, then no need to look at even other options, but we'll look at it. Deciding whether given string generated by given context free grammar, This is decidable because CYK algorithm is there for this. For the context free grammar, to check the membership concept, right? So you have the CYK algorithm. Deciding if language generated by given context free grammar is empty. Emptiness, you can use a simplified grammar. You can use simplification that will help you. It's decidable. And deciding if the language generated by given context free grammar is finite. You can use a dependency graph that will help you whether the grammar generates, context free grammar generates finite or infinite language. Dependency graph. Construct the dependency graph and check for the loops. That would be sufficient. So only option A. Yeah. Yeah. Can you try the next one? This is the where you need to put an effort. So far all the questions were easy, but this question is the next level question. Many people can say this is undecidable, but may not able to answer it. Is it partially decidable or not? So where you need to put an effort. Let M be the encoding of Turing machine string over 0 and 1. Let L is a set of all Turing machines where M accepts a string of length 2014. So whether given Tm accepts a string of 2014 length, can you find, right? First, that is very important. Whether is M accepts 2014 length string. Any string is fine. Do you have any? For this, the M is given to you. That's it. M is given. The Turing machine is given. Now you need to say yes or no. Who will have a logic? If really accepting some 2014 length, you will definitely halt at final, and you can find out because only finite number of strings are there with 2014 length. So you can create the threads for every string, and you can check is that any string halts at for any string some thread halts at final or not. So this is you can find a logic. Logic exists. Logic exists. If you are saying that the M is not accepting 2040 length, that means every string, if it is able to halt at non-final, you can decide. But many strings might go never halt. Some this Turing machine may never halt for some 2014 length. Then the no, saying no is very difficult. When will you say no? For every 2014 length, the Turing machine halting at non-final, you can say. But no guarantee that it will halt at non-final. It may go for never halting case. So this is not going to have a logic. Logic not exists to say no. That's why S only has a logic here. S only has the logic here. S only has a logic, and no is not having a logic. That makes even the problem is undecidable, but it is partially decidable. Which one makes that undecidable but recursively enumerable? This is called as partially decidable, semi-decidable, undecidable but are recursively enumerable. You can't say decidable, you can say undecidable, but you can't say not real, and decidable you can't say. So only B. Second option is right. You can't say it is decidable, even though it is real, but you can't say decidable. So the second option is also called as undecidable but semi-decidable. This another name for RE is a semi-decidable, SD. Okay. Yeah. L and L complement. Which of the following is not a viable possibility? Okay. Just try. Not possible. Simply just look for not possible. Yes, different, Sham. Yes, both are different. Every decidable you can say partially decidable, but partially decidable need not be decidable. Simply partially decidable, another name is recursively enumerable. Decidable, another name is recursive. So even you are able to understand recursive, right? That's same as decidable. But recursively enumerable is same as partially decidable, semi-decidable. You know already recursive RE, right? Same way these two are recursive another name and RE another name here. Okay, just synonyms they are. Okay, partially decidable also called as recursively enumerable. Just remember that way, you can easily understand the concept. Now, not possibility, not possible. Which of the following is not possible? Check. L and L complement both are not RL. Is it possible? Yes, possible. When sometimes not RL complements are also not RL. In that case, this is possible. Okay, just you need to find not possible case. L and L complement, one of them is RE but not recursive. See here, this is important. RE but not recursive. One of them, either L or L complement, and the other is not RE. Yes, exactly, that is right. If any one of them is RE but not recursive, its complement has to be not RE. This is also possible. Because we know RE but not recursive complement is not RE, we have seen a lot of examples. Both L and L complement are RE but not recursive. Impossible. We know that RE but not recursive, its complement never be again RE but not recursive. So this is impossible. This is impossible. You cannot find even single example in the world both L and L complement are in the RE but not recursive class. Okay. Last one, both L and L complement can be recursive. Of course, one of them is recursive complement, definitely recursive. We see infinite example for them. It's always if L is recursive, L complement is always recursive. So this is possible. So only C, only C. Yeah, only C. Correct. Sima Sham, correct. Yeah. Which of the following are undecidable? Easy question, right? Very easy. See how easy undecidability topic. If you have the basics, you cannot take even more than 1 minute. Hardly it takes 1.5 minute. Just read and you will understand immediately when you have the basics clearly. So this is the time saver topic. Learning may take time, but in the GATE exam, it saves your whole time for the questions. Okay. But never predict the answers when you don't understand. Better to ignore the question if you don't know the concept at all, and if you are good at undecidability understanding, you have studied very well, then better attempt this question and save this time and get the good marks and go for other question to spend more time on difficult questions. Yeah, this is emptiness problem. Emptiness problem for context free grammar is decidable. We know, we are aware of that. And totality problem for context free languages is undecidable. Turing machine, see how many times this question came so far, right? It is undecidable. Repeated question. And DFA and NFA, and you are simply asking equivalent. Given DFA and NFA are the equivalent, yes, both of them you can convert to, or you can apply the algorithm on DFA to get a minimum DFA. You can also apply algorithm on NFA to get a DFA, then minimum DFA. So once you got the minimum DFAs, are they same? Are they isomorphic? Then they should accept same language. Okay. So you have an algorithm for this, so it is decidable. So only two problems, 2 and 3. 2 and 3 are undecidable. 2 and 3 are undecidable. 2 and 3. That's going to be option D. Yeah, 1 and 4 are decidable, and question is about undecidable, so 2 and 3. Okay. Yeah, can you try this? Which of the following statements are false? See how easy the questions from undecidability. First one, every NTM there exists equivalent DTM. Yeah, they are equivalent, right? Every NTM you can convert to DTM, every DTM you can convert to NTM. So this is a true. Turing recognizable languages are closed under union and complement. Recognizable in the sense it is RELs. RELs are closed under union and complement is wrong. Yeah, is voice clear to everyone? Yes, Seema, Sham. Is that audio clear? Any issue with the audio and video now? Yeah, clear. RELs are closed under union but not closed under complementation. That is the reason this statement is a false statement. Okay, you need to identify the false statement only. This is not a true statement. Only half of the statement is true, but whole statement is false. Turing decidable languages means recursive languages are closed under intersection and complement. Yes, it is true. It is true. Recursive languages. Decidable means recursive. Recognizable means it is REL. Okay. Turing recognizes RELs. Turing decides recursive. Turing recognizable languages RELs are closed under union and intersection. This is a true statement. So you are going to identify false. False is only the second statement. That is only that option C. Option C is a false. Now you need some homework questions, right? So I'm giving some homework questions to practice. Please go and practice after this session. Please practice these questions and answer it. They might be very easy. Okay. When they ask about like a program, just assume it is a Turing machine. Okay. Program, machine, grammar. When they don't mention anything, that is going to be a Turing machine concept. Okay. First question. And second question, that again operations oriented. Third question, yeah, problems. You need to identify decidable problems here. And this is a very straightforward question. Definition of somebody here. You can easily find out who is that. And fifth one, prime concept, set of prime numbers, or right, the set of prime numbers, or you can say a power prime. This language is what? Yeah. And exactly, yeah, you saw right. So many gate questions, all the gate questions are very straightforward, except either here and there. Maybe I have not included some questions here, but here and there you see one or two questions which may take time, but most of the questions just read and answer it based on the problems and properties. They are going to be very easy. DBMS by Vijay sir, this is the next subject. Anybody want to learn DBMS, and definitely you will enjoy a lot from Vijay sir. Going to start from day after tomorrow, 29th March. Timings 4:30 p.m. to 5:30 p.m. Anyhow, this class will be scheduled soon. I think it might be scheduled already, or if not, it will be scheduled soon. So please check the classes. Yeah, I'll take the classes. Compiler design will, classes will take after some time. Okay, not now, because there are many subjects that you have. So let them continue, and then I'll come in the middle to start the compiler. Okay. Yeah, thank you everyone who joined now, and see you. Take care. Bye bye.